Tonight, the moon is gone. In its place hangs an entire planet, nearly twice as wide in our sky and glowing red above the horizon. But before anyone finishes taking the perfect photo, the oceans begin moving. Mars is almost 9 times more massive than the moon, and Earth is about to discover that its new neighbor is far too powerful to ignore. And the tides are only the beginning. To explore this impossible thought experiment, we must assume Mars is placed at the moon's average distance of 384,400 kilometers, while the rest of the solar system initially remains unchanged. This is not a forecast, but a study of pure physics. At 6,790 kilometers wide, Mars is about twice the moon's diameter. In our night sky, it would appear nearly twice as wide and cover almost 4 times the area, spanning about 1 degree of the horizon. Reflecting sunlight with a slightly higher albedo than our old moon, the red planet would cycle through familiar waxing and waning phases, its crimson glow brightening or dimming throughout the month. Under favorable conditions, observers on Earth could detect broad albedo changes, catching glimpses of major landmarks like the massive volcano Olympus Mons, the vast canyon of Valles Marineris, polar ice caps, and giant dust storms. However, these surface features would appear soft and broad, lacking the sharp clarity of satellite maps or telescope photographs. Stargazing would become easier, mostly because one planet would be aggressively occupying the view. But a celestial neighbor of this scale brings far more than a spectacular sky. We must look past the glowing red dust and consider what its massive weight means for our home. For this cosmic arrangement to function, Mars must travel at a precise circular orbital velocity of about 1 kilometer per second. Because Mars is nearly 9 times more massive than our moon, approximately 8.7 times, to be exact, it would refuse to play the role of a passive satellite. Instead, Earth and Mars would instantly lock into a genuine double-planet system, spinning around a shared center of gravity known as a barycenter. This point would sit roughly 37,000 kilometers from Earth's center, meaning it is positioned well outside our planet's surface. Think of 2 dancers spinning while holding hands, except here, both dancers are entire worlds. As they loop around this empty point in space, Earth's own wobble would become measurable and constant, completed in an orbital cycle of about 26 days. While this initial, perfectly circular setup is an artificially imposed starting condition rather than a natural capture, the mathematical laws governing their orbital motion are entirely real. The monthly calendar would still exist, but it would have a much more serious dance partner. This constant orbital tug-of-war alters the very balance of our planet, starting with the massive bodies of water that cover our surface. Tidal force depends on the mass of an object and its distance, scaling approximately as mass divided by distance cubed. Because Mars is nearly 9 times more massive than the Moon, placing it at the same orbital separation increases the gravitational pull on our oceans. As a simplified estimate, Mars would generate roughly 9 times the Moon's tidal influence. However, this stronger force does not mean every local tide simply becomes 9 times taller. The actual behavior of the water depends heavily on ocean depth, coastline shape, and basin resonance. While some areas might damp the incoming energy, others would dramatically amplify it. In an uncertain simulation of this double planet system, there is no instant global tsunami wrapping around the Earth. Instead, we would see a chaotic, ongoing cycle of water adjusting over hours and days, driving massive surges and powerful currents through ocean basins. Low-lying ports and coastal cities would face regular, severe flooding. Beachfront property would remain expensive, mainly because you might need to buy it again every month. These massive shifts in water level would disrupt global shipping, drowning modern docks and rendering harbors unusable. As seawater pushes farther inland, it would invade coastal wetlands, contaminate freshwater aquifers, and alter the salinity of rivers. Marine ecosystems would face immediate disruption, as intertidal species are subjected to extreme cycles of deep submersion and dry exposure. The sheer volume of water moving across the globe would generate enormous friction. Over time, this relentless sloshing of the oceans begins to transfer its kinetic energy, shifting the burden of Mars's gravity from the water down to the solid planet itself. The oceans are not the only parts of our world that respond to Mars's massive gravitational embrace. The solid Earth itself deforms under ordinary tidal forces, but this new arrangement greatly increases that gravitational flexing. As Mars loops around us, it exerts additional geological stress on Earth's crust, constantly squeezing and pulling the planet's rocky interior. While tectonic plates still control major earthquakes, computer models of this uncertain simulation suggest this added stress could trigger timing shifts in already loaded fault lines, or cause minor regional volcanic variations. However, there would be no instant crustal rupture and no universal volcanic eruptions. Instead, this relentless flexing transfers Earth's rotational energy into internal heat and orbital motion. Over geological timescales, tidal friction would gradually slow Earth's spin, slowly stretching our calendar. The day would get longer, but not long enough to excuse being late for work. Because changing ocean geometry alters how this energy is lost, the exact long-term rate remains difficult to predict. But while our planet absorbs this heavy gravitational pull, we must ask, how does Mars respond to the very same exchange? Earth exerts a massive gravitational grip on its new partner. At this close distance, our planet pulls on Mars with a force far stronger than anything its tiny native moons, Phobos and Deimos, could ever muster. Computer models suggest this intense gravitational tug-of-war could cause significant internal flexing within Mars, triggering deep Marsquakes and generating internal friction. This friction might warm the Martian mantle, perhaps even sparking localized volcanic activity in thin crust regions. Yet, despite these dynamic geological stresses, Mars remains a fundamentally hostile desert. Orbiting at our distance means Mars receives more than 2 times its usual solar energy, but more sunlight does not magically create a habitable paradise. The Martian atmosphere is still a thin whisper of carbon dioxide, exerting a surface pressure of just 6 millibars, less than 1% of Earth's. Without a thick atmosphere or a protective global magnetic field, the surface is constantly baked by lethal cosmic radiation, and liquid water would still instantly boil away. Mars would finally become easy to visit, but walking outside without a spacesuit would remain a very short hobby. Survival would still depend entirely on pressurized habitats, heavy radiation shielding, and artificial life support. When Mars passes directly between Earth and the Sun, it blocks the light. Because Mars appears twice as wide as our Moon, it easily swallows the solar disk. This block of light creates a massive solar eclipse, revealing the Sun's glowing corona around the dark silhouette of the red planet. On the ground, a broad shadow sweeps across entire continents, turning day into night. Conversely, when Mars passes behind Earth, it plunges into our shadow, turning a vivid crimson. These events are not daily occurrences. Their timing and locations depend on the shape and tilt of the orbit, creating a periodic cycle that differs from our present lunar calendar. Eclipse photographers would need a bigger calendar, and probably a much larger hard drive. With Mars sitting just 4,400 kilometers away, interplanetary space travel becomes a local commute. Radio signals that once took up to 24 minutes to cross the solar system now flash back and forth in a mere 2.6 seconds. This near-instant communication allows scientists on Earth to pilot robotic rovers on the Martian surface in real time, turning delay-heavy exploration into live, active discovery. But while talking to Mars is suddenly effortless, physically landing on it remains a brutal physics problem. Sending a spacecraft to this new orbit requires the same basic launch energy as an Apollo mission. However, once you arrive, the old lunar spacecraft are completely useless. Mars is heavy, with an escape velocity of 5 kilometers per second. Landing requires heavy heat shields to survive atmospheric entry, and launching back into orbit demands enormous rockets packed with fuel. Still, having a planetary neighbor this close changes everything for safety. For the first time, Mars rescue could mean prepare immediately instead of check the calendar for next season. Pressurized bases, once a distant dream, now seem like practical next steps. Yet, as engineers draw up plans to visit this new world, our double-planet system faces a much larger silent test. This final test is a matter of orbital insertion. For Earth and Mars to coexist, the red planet must arrive at a precise position, moving in the exact right direction at a highly specific velocity. Any deviation makes this arrangement impossible. If Mars approaches with too little speed or at an incorrect angle, the trajectory leads to a direct, cataclysmic collision with Earth. But if it carries even a slight excess of arrival speed, Mars will break free from Earth's gravitational grip entirely, escaping into its own independent solar orbit. Even minor insertion errors could result in a highly eccentric orbit, destined to destabilize both worlds. Long-term orbital stability remains an uncertain simulation, heavily dependent on solar perturbations, orbital inclination, and gravitational resonances. While a perfectly executed insertion avoids immediate planetary destruction, a surviving planet is not the same as an unchanged society. We would still face ongoing tidal flooding, ruined coastal infrastructure, and a permanently altered day. Ultimately, this delicate orbital stability is the only line separating a functioning double-planet system from the shortest, most spectacular astronomy experiment in history. Mars replacing the Moon would create the most beautiful night sky humanity had ever seen, and possibly the most dangerous coastlines Earth had ever experienced. We would gain an entire planet within reach, but lose the quiet gravitational balance that shaped life for billions of years. So the next time the Moon looks small, remember, that may be exactly why we are lucky. If Mars appeared in our sky tonight, would you remain on Earth or volunteer for the first mission to our new neighbor? Tell us in the comments and subscribe for more cosmic what-if scenarios.